Does time really exist? Our brains don't actually have a built-in clock, which is why 5 minutes on social media feels a lot shorter than 5 minutes staring at a wall. Albert Einstein, one of history's greatest physicists, once challenged the notion that time was linear. He said that if you put your hand on a hot stove for a minute, it would feel like an hour. But if you sat with someone you liked for an hour, it'd feel like a minute. What Einstein meant was that time is relative to each person and situation. So, the big question is time just something humans made up? Our experience of time varies based on factors like attention, emotions, and memories. After all, time flies when you're having fun. Studies even show that time seems to move faster the higher up you live. Interestingly, time isn't controlled by a single part of our brain. Instead, multiple areas, like the hippocampus, cerebellum, and frontal cortex, all play a role. We also sense time based on how our bodies feel. Depending on the time of day, we might feel energetic, sleepy, or hungry, thanks to our body's internal clock, known as the circadian rhythm. This 24-hour cycle helps us stay aware of the time and manage our daily functions. Even animals like goldfish and dogs can sense time. They know when it's time to eat, even without understanding the concept of hours and minutes. This shows that our sense of time goes beyond just clocks and calendars. Time is everywhere. In the changing seasons, the sun rising and setting, and in how we age. It moves forward from the past to the present and into the future. Famous physicist Stephen Hawking talked about how time has a direction, always moving forward. But then, do the past and future really exist? Our view of time is tied to what we experience in the moment. For a long time, people thought time flowed from past to future in a constant way across the universe. But in 1905, Einstein introduced his theory of general relativity, which showed that time isn't the same for everyone. According to his theory, time depends on how fast you're moving, and this idea is known as time dilation. However, the direction of time is the same for everyone. Einstein also came up with the idea that time and space are linked together in a fabric called spacetime. This fabric can bend around objects with a lot of energy, like the sun, which is why planets orbit around it. This bending creates what we call gravity. Time doesn't flow the same way when we look at it on a cosmic scale versus a biological one. In the space-time continuum, there's no clear-cut now that applies to everyone. And someone's now might be different from yours because of how time and space interact. In the special theory of relativity, there is no absolute time. It is different for each observer. However, there is a concept of proper time, the time measured by a clock following a particular line in four-dimensional space-time. The lives of each of us are these trajectories, and while on the one hand, time is not unique, on the other hand, for the given observer, time is unique. So, while time seems to exist, it's also a social construct we've created to help organize our lives. We measure events in seconds, minutes, and years to keep things in order. Without time, our modern world would be chaotic. Despite the latest findings in physics, the fact that we still rely on time in science and our daily life shows that time is more than just a social construct. And even if time is eventually proven to be an illusion, it's still a crucial part of how we live and understand the world.
Time runs like a river. It has direction, always advancing. It has a certain duration, periods between events you can measure. Time feels real, always there, unstoppable, moving forward. But what if I told you that time might not exist? Some physicists and philosophers claim that there might be no such concept as time, and we should take this possibility of the non-existence of time seriously. You see, recently, physics has been in crisis. For the past century or so, two extremely successful physical theories have been used to explain the universe. Those are the theory of general relativity and quantum mechanics. Quantum mechanics describes how things work in the super tiny world of particles and their interactions. As for general relativity, It provides an outlook on the bigger picture, for example, gravity or how objects move in space. And even though both of these theories seem to be working really well, they are believed to conflict with one another. That's why some scientists think that they need to be replaced with a new, more general theory, like quantum gravity. This idea might be able to explain how gravity works at the miniature scale of particles. Apparently, it's incredibly difficult to produce the theory of quantum gravity, but it might be possible to do it with the help of string theory. It replaces particles with strings, vibrating in 11 dimensions. But there's one problem. Even though string theories do provide several models describing the universe, they don't make any clear predictions that can be tested by experiments to understand which model is the correct one. There's one more idea known as loop quantum gravity. According to it, the fabric of space and time is made of super tiny chunks, loops. But the most remarkable aspect of this theory is that it completely eliminates the concept of time. Now suppose this idea turns out to be correct. Will it mean that time doesn't exist? Well, the answer is kinda complicated. Everything depends on what the word exist means. A philosophy professor from Cambridge University claims that the three basic properties of time, a present moment that is special, the flow of time, and its direction, come from our mental states and not from the physical world. So we sense this arrow of time because our minds add a certain subjective ingredient to reality. At the same time, Einstein's theory of relativity supports the idea of the block universe, a four-dimensional space-time structure where time is like space. It has its own coordinates in space-time. Time is tenseless there. Thus, the future and past are as real as the present. Does it mean we're being fooled by our human perspectives? Is the feeling that time passes and has a certain direction false? Well, we can imagine our world as a three-dimensional place where stuff happens gradually over time. Or it might be a four-dimensional space where nothing actually happens because nothing changes. It's all here at the same time, past, present, and future. The main idea of relativity is that there's no absolute space and no absolute time. Everything is relative. Trying to think about time in the context of the universe, you realize that you need to isolate part of it and call it, let's say, your watch. And time is basically the relationship between some parts of the universe and that thing you called your watch. Another scientist says that time is just a collection of snapshots describing our reality while continuously changing one into another. Here, you hit play. Here, you're blinking while watching this video. And here, you're taking a sip of your coffee. Without these changes, there wouldn't be any notion of time. The changes are real, but time is not. Our brain sees these changes and constructs a sense of time, believing that it's flowing. What do you think? Is time just a social construct, or does it really exist?
The morning is cloudy, but it isn't raining. So you grab your bag and head off to work. You're halfway there when it starts drizzling, then raining, then pouring. There's only one thought in your head as you're dashing through wet streets towards your office building. If only I could hop in a time machine and go back in time. I'd have put that umbrella in my bag. Unfortunately, going back in time is not possible. But guess what? We still managed to travel in time. But let's start from the very beginning. More than 100 years ago, a famous scientist called Albert Einstein, I bet you've seen his most popular photo, came up with a theory about how time works. He gave it a nice little scientific name, the theory of relativity. According to it, space and time are linked together. Another point is that our universe has a set speed limit. Nothing can move faster than the speed of light, which is 186,000 miles per second. Okay, you may say, but what does it have to do with time travel? Well, the theory of relativity also claims that the faster you move, the slower you experience time. And several experiments prove this to be true. For example, let's say you have two clocks set to the exact same time. You leave one clock at home and take another one with you while traveling by plane. What's important here is the fact that the plane is going in the same direction as Earth. After your plane finishes its flight around the world, you can compare the time on the two clocks. You find out that the clock that traveled with you is a bit behind the clock that remained on the ground. Because of this, GPS clocks are corrected. GPS satellites travel around our planet at tremendous speeds, around 8,700 miles per hour, and more than 12,000 miles above the surface of Earth. This speed slows GPS satellite clocks down, but the altitude speeds them up. As a result, the clocks on GPS satellites experience time at a rate that is slightly faster than 1 second per second. And if this difference in time wasn't corrected, you wouldn't be able to use GPS to figure out your exact location. In any case, this is probably the closest thing we have to time travel. You see, our planet is constantly moving around the Sun at an average speed of 67,000 miles per hour. The Sun, along with the entire solar system, is, in turn, circling the center of our home Milky Way galaxy at a staggering 140 miles per second. And the Milky Way itself is also moving. It's spinning at a speed of 130 miles per second. Those are some really dizzying numbers. And now imagine that in order to get to the past, all this space matter must also turn back and return to its original position. Just admit it, it's absolutely impossible. By the way, even though we can't exactly travel back in time, we can look at the past, thanks to NASA's space telescopes. They help us see stars and galaxies that are insanely far away. It takes the light coming from them ages to reach Earth. That's why when you observe those distant worlds, you see what they looked like a long time ago. Now, what if time travel was somehow possible? Wouldn't all the fun be spoiled by the time travel paradox? You know, like finding yourself in the past and accidentally preventing your parents from meeting each other? The problem is that Einstein's theory of general relativity theoretically allows a person to travel back in time and come in contact with their past self, which can potentially endanger their existence. But you can breathe out. Some scientists at the University of Queensland have recently claimed that this paradox might not actually exist. They say that even if you made some changes in the past, the timeline would self-correct anyway. In other words, it would still ensure that whatever event sent you back in time would still happen. One more study claims that even if some changes happened in the past, they wouldn't drastically alter the future. Imagine, you're on a vacation and your hotel reservation gets cancelled. Bummer. You'll have to find another place to stay, right?
Yeah.
You start Googling for accommodations when you stumble upon this ad. It mentions a hotel that seemingly has an infinite number of rooms. They'll surely have a room available for you, right?
Oh, yeah.
You arrive at the hotel and you're greeted at the check-in desk by the hotel manager. This receptionist in particular sure does look special. You'll soon find out why. He starts by saying all his rooms are booked. The infinite number of rooms are all filled by an infinite number of guests. But wait, the manager might have a solution to still check you in. Told you he was special.
Oh, yeah.
He begins to explain that all the rooms in the hotel are numbered, starting from room number 1. It goes on to room number 2, then 3, moving forward infinitely. At this hotel, there is only one person allowed per room. So if there is one person in each one of the rooms, how will he make space for you? Simple. He asks each one of the guests to move down a room. This way, the person staying in room number 1 moves over to room number 2. That person in room number 3, and so on. Once every one of those infinite numbers of guests moves down a room, the first one becomes available for you to stay.
Ooh,
While you're waiting at the reception, a bus shows up, wanting to check in too. 100 guests are waiting inside the bus. The receptionist applies the same strategy. He moves everyone down 100 rooms until the first 100 rooms become empty and ready to receive guests. Word rapidly spreads around that there's a hotel that can fit a lot of guests. Obviously, more buses like this one start to arrive. And they're not just a lot of buses. An infinite number of buses with an infinite number of passengers get lined up at the hotel entrance. Our receptionist is clever yet again. He opens his infinite agenda with an infinite number of pages and starts preparing a table. This one too has an infinite number of columns and rows. In this table, there's a row for each bus, with the row at the top for all the people that are already in the hotel. He uses the columns to show the position each person occupies. He's got room number 1, room number 2, and so on. He moves on to fill the table with bus 1, seat 1, then bus 1, seat 2. His goal is to make sure each person gets their unique code. This code is made out of a combination of the vehicle and the seat number. He then proceeds to show everyone how he'll assign the rooms. Starting with the top left corner of his table, he draws a line that zigzags back and forth across the table, going over each person exactly once. If he could pull at that line from each end, he'd transform an infinite by infinite table into one single row. Once the order from that line is defined, he assigns each room number to its designated visitor. Everyone fits once again. Just as our brilliant receptionist is about to take a break, a big bus appears at the hotel entrance. Not a regular vehicle, but a party bus. It has no seats. But as you can already imagine by now, this one has an infinite number of passengers too. As they step down from the bus, you listen to their names. They sure are weird. Soon enough, one of the new party visitors starts to explain why they call each other the way they do. Since there's an infinite number of them in the bus, they've all decided to use unique identifiers, only using the letters X and Z. To keep with the theme, these names are also infinitely long. One person might be named XXXXXXXXXX, with letters going on indefinitely, while another may be named XZ, 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 XZ again, with its name going on forever. After thinking about it for a bit, you figure out that there's a person for each possible infinite sequence of these two letters. But just as the people from the party bus start entering the hotel, the receptionist says that he's not able to fit all of them into the hotel. "It might be a bit complicated to explain this time," he says, "but let me try." He starts by opening up his infinite agenda once again. He then proceeds to assign rooms to the people on the bus. Let's say room number 1 is for the person named XXXXXXXXXX, while room number 2 is for the person named XZ, 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 XZ. To finish up, he'd technically have to keep going, allocating a different string of X's and Z's to each of his infinite number of rooms. "Here's where it gets tricky," he says. "Because even if we complete this infinite list of names, I can still name a person who won't be assigned a room." All you have to do is to figure out who that person is to take the first letter of their name and switch it, so X becomes Z. Then you take the second letter of the second name and switch it from Z to an X. If you keep doing that, the name you write down is surely not going to appear on the list. You might have stumbled upon a hotel with an infinite number of rooms, but that's not to say it can fit literally everyone, because those rooms are infinite, but they are countably infinite. Even if it would take forever, you could technically count all the rooms in the hotel. The reason why you can't squeeze all the people from the party bus is that those people are uncountably infinite. There's no systematic way to identify them. When you look at it this way, it does make you think, are some infinities bigger than others? This theory is called David Hilbert's Infinite Grand Hotel, and it's not the only one of its kind. The friendship theory is a funny one too. It means that most people have fewer friends than their friends have.
Hello.
So, if you have 3 friends, chances are that your friends have more than 3 friends each. It's like a puzzle. It's hard to figure out why this happens, but it's true. It was first noticed back in 1991 by a sociologist named Scott Feld. He made this unusual discovery when looking at existing social networks. He calculated the average number of friends that a person has and then compared this number to the average number of friends those respective friends had too. The interesting part happened when he noticed the second number is always bigger. Problem is, there's no logical explanation for this phenomenon. Why is this important, you might ask? Because it affects the way we perceive ourselves in relation to others. Most of us look at our friends as being happier, richer, and more popular than they are. But it's important to remember that almost everyone is in the same situation. Then, there are Zeno's theories, which are puzzles about motion. They ask questions like, if you have to take half of the steps to get somewhere, and then half of those steps, and then half of those steps, will you ever get there? The answer is yes. Even though it might seem like you'll never get to the end, if you keep taking half of the steps, you will eventually get there. It may seem weird, but all these theories are in fact paradoxes. In math, there are mathematical conclusions so absurd that it's difficult to understand, even though every step you took before reaching that said conclusion is correct. In most scenarios, the paradox is the contradiction of the statements themselves. In David Hilbert's Infinite Grand Hotel, for example, these statements are that the hotel can be fully booked and have rooms available at the same time. Scott Kelly is a lot of things. An American engineer, a retired astronaut, and a time traveler. Wait, what? Kelly commanded the International Space Station on several missions. On one of those trips, he spent 340 days aboard the giant, floating science lab orbiting Earth. While he was up there, improving the water recycling system, testing heat transfer in microgravity, and doing all the other genius-level stuff astronauts do, he was also aging. But not like you, me, or even his identical twin brother Mark. He was actually aging slower than all of us. Okay, so both brothers are astronauts and have been to the International Space Station, but Scott spent way more time up there. About 10 times as long, actually. And here's where things get more interesting. Even though Mark was born 6 minutes before Scott, he is now 6 minutes and 5 milliseconds older. That happened because Scott aged a little more slowly while he was orbiting the Earth. And astronauts age slower because they're moving much faster than us, at 17,500 miles per hour. Basically, the faster you go, the more time stretches out. So the closer you get to traveling at the speed of light, the slower you age. From Scott Kelly's perspective, nothing felt unusual up there. Time passed like normal for him. But he actually aged less than his twin brother over the same period of Earth time. So when he returned, we can say that he had essentially leapt forward in time relative to us. So, if traveling close to the speed of light lets us leap forward in time, that means astronauts have already kind of achieved time travel. Sure, it's a bit of a letdown that it doesn't happen like Back to the Future, you know, hopping into a cool futuristic car and zipping into another timeline. But this is real, at least according to some scientists. Real time travel isn't about jumping from one moment in time to another, like going back to the age of the dinosaurs, then hitting a button to fast forward to the year 2100. The time travel that's possible today is more about actually living into the future. It's about moving faster than 1 second per second, just like Scott Kelly did. To explain the theory behind this wild idea, we have to bring a celebrity into the conversation: Albert Einstein. Think about your childhood and your retirement. Whether it's in your past or your future, time always ticks at the same steady rate. But then along comes Einstein saying, sure, but it's not that simple. He introduced the idea that time is relative. In other words, the amount of time you experience compared to someone else depends on what you're both doing. And where exactly you are in the universe. Time is not the same for everyone. Here's an example. You're sitting on a bench, holding a melting ice cream cone. Meanwhile, your friend zooms past in a super fast spaceship. For you, maybe the ice cream melts in 5 minutes, but for your friend flying at a crazy speed, this same scene took less time on his watch. That's time dilation. time actually moves slower for things that are moving faster. That's the heart of what's known as special relativity. We actually proved Einstein's theory back in the 70s. Two scientists took super accurate atomic clocks and flew them around the world on planes, first going east, then west. They compared those clocks to a third one that stayed on the ground. When all three were brought back together, they showed different times. The clock that flew east in the direction of Earth's rotation lost 59 nanoseconds, and it was moving faster relative to the ground. The one that flew west against Earth's rotation was moving slower, so it gained 237 nanoseconds. Now, think about those astronauts living in space moving way faster than we are. They travel at about 5 miles per second, orbiting Earth roughly every 90 minutes. If you do the math, spending 1,000 days up there lets you skip about 0.027 seconds into the future. I know that doesn't sound like much, but that's because the speed of the ISS is tiny compared to the speed of light. Still, if we keep going with that idea, it pretty much makes the astronaut Oleg Kononenko humanity's greatest time traveler. In 2024, he set the world record for the most time spent in space: 878 days in orbit. Okay, so we now know that Kelly and Kononenko are, in a way, living in the future. But what about traveling backward in time? Well, I'm sorry to say, traveling back to your glorious high school days is a whole lot trickier. In theory, we could, but in practice, it's pretty much impossible. Imagine space and time as this big, stretchy fabric, and gravity is what bends it. Kind of like when you put a heavy bowling ball on a trampoline. In theory, if you could bend it just right, you might create a shortcut through space and time called a wormhole, a tunnel that connects two different points. Let's say the present and the past. Now, usually, gravity pulls things inward. It wants to collapse tunnels, not keep them open. So the walls of this tunnel are constantly under pressure from the universe, trying to squish them shut. To stop that from happening, and to keep the tunnel open long enough for something or someone to go through and get to the past, you'd need something that pushes outward, against the collapse. And that's where negative mass comes in. Negative mass is a weird, theoretical idea in physics. Unlike regular mass, which pulls things together with gravity, negative mass would actually repel things. It would push away instead of pulling in. It's like using anti-gravity to keep the tunnel from closing. It would act like braces, holding the tunnel open from the inside. But here's the problem. We have never actually seen negative mass. It's just something that might exist on paper, in math, but no one's ever found any in real life. Plus, there's something called the self-consistency principle. Basically, it says that time travelers can't create time paradoxes, like those crazy scenarios in the Butterfly Effect movie. Let's say you go back in time to stop your granddad from meeting your grandmother. But here's the problem. If they never met, that means your parents were never born. And if they weren't born, well, how do you exist? That's a time paradox. Something that causes all sorts of inconsistencies in the universe, making everything a total mess. And according to the self-consistency principle, that's impossible. It just can't happen. Some specialists, though, think they have an answer to the grandfather paradox. All we need to do is think about time as an endless loop with no starting point. In a closed time-like curve, as this theory is called, the past and present blend together in an eternal time loop. There's no way out. There's no changing things. It would all look the same if played in reverse. For example, what did you do yesterday? Let's say you woke up, brushed your teeth, worked all day, had your meals, and then went to bed again. Following the closed timeline curve theory, if you could go back to yesterday, you'd do those exact same things in the same order, no matter how hard you try to take the day off. because in a closed time-like curve, you're retracting not just your steps, but every single second of reality itself. And that's the only way time travel could be possible. So, even if we somehow manage to build a time machine, and even if we give it our best shot to change the past, nature will always find a way to prevent contradictions. In the end, everything would have to align perfectly to keep our history from becoming a mess.
Guess what? The universe can get actual scars, just like when you fall off a bike. Well, here's why. Before the Big Bang, the universe was extremely hot, dense, and full of energy, and it seemed like everything was going well, until that all changed about 13.8 billion years ago. Then the universe exploded. After the blast, it expanded incredibly quickly. Our human brain can't even perceive how fast that expansion was. Sometime later, the universe started cooling down. As it did, giant, terrifying scars cutting through space-time appeared all over the place. And if we study these scars well, we can even get insight into time travel. These days, we call these scars cosmic strings. They're like stretch marks that appear when the skin expands too quickly. Or we could also compare them to cracks that form in the ice when it freezes. These strings are likely very thin, about the size of a proton, a positively charged subatomic particle. Yes, subatomic means smaller than an atom. The strings are also extremely dense and can stretch for light years. Now, imagine these cosmic scars floating through space, not interacting much with their surroundings. When two cosmic strings pass each other, they could warp space-time in such a way that it creates a time machine. If you were to travel along a certain path around these strings, you would end up returning to your starting point at an earlier time, which is traveling back in time. Now, let's admit it, this idea sounds like something from science fiction, but it's supported by cosmic string theory, and the math behind it seems to work. Unfortunately, no one has observed cosmic strings yet, so for now, it's still a theory. In 1991, one physicist proposed an idea for how cosmic strings could enable time travel. If two infinite cosmic strings passed each other in parallel, they would warp space-time, creating a time loop. This loop would allow someone to travel back in time. Even better, this idea doesn't contradict Einstein's theory of general relativity, which suggests that large objects can bend space and time. These bends in space-time could allow a shortcut through time. His now well-known concept of closed time loops also helps explain how wormholes might work. So, a wormhole is basically a theoretical tunnel connecting one place in space to another. Some people believe that by using such tunnels, we could create shortcuts for incredibly long journeys through the universe, which would allow us to visit other star systems and galaxies. So, let's say you manage to create a wormhole and even accelerate one of its ends to near the speed of light, and then you send it back to where it came from. Well, at that moment, those two ends are not synced anymore. One is in the past, while the other is in the future. And if you somehow manage to walk between them, you'd be time traveling. You could do something similar by placing one end of the wormhole near a powerful gravitational field, like a black hole, and keeping the other side near a weaker gravitational force. This way, according to the theory of relativity, time would pass more slowly nearer to the strong gravity side, and it would allow a particle or another chunk of mass to remain in the past relative to the other side of the wormhole. At the same time, if you decided to create a wormhole, you'd have to keep in mind that they are super dangerous. They might collapse all of a sudden. They're likely to be highly radioactive, or you could come into contact with toxic exotic matter inside. But let's get back to the math behind the cosmic string time machine idea. Admittedly, it is solid, but it doesn't mean such a time machine is possible yet. To use this way of time travel, we'd need to reach near light speed, and it might be impossible. According to Einstein's relativity, the faster an object travels, the more energy it needs to continue speeding up. In other words, we don't yet have the technology or energy sources to accelerate a spacecraft to these speeds. The idea of two infinite cosmic strings is also questionable because we can't create something that's infinitely long. So, while this time travel model is mathematically sound, the infinite nature of the strings would make this exact model impractical. At the same time, some scientists still believe that cosmic strings are a better possibility than most other models, like wormholes. In any case, before we can start considering time travel, we need to discover cosmic strings. Luckily, there's a group of astronomers working to detect low-frequency gravitational waves by measuring signals from a type of star called a pulsar. Now, pulsars send out regular pulses of radio waves, and by measuring small changes in the timing of these pulses, scientists can detect subtle shifts in space-time. Those changes are caused by gravitational waves, which are ripples in space-time. Now, so far, we've only detected gravitational waves coming from black holes. But in 2020, there was one strange signal that didn't look like it came from black holes. It could be coming from cosmic strings. And here, we need to mention string theory. According to it, the universe is made up of more than just the 4 dimensions of space-time. There are additional dimensions that are hidden from us. Plus, the basic building blocks of the universe aren't particles, but tiny vibrating strings. These strings can vibrate at different frequencies to create different fundamental particles. These strings, from string theory, could have stretched out during the early universe and become the very cosmic strings we've discussed. In the coming years, we might get more information about them from a space-based gravitational wave telescope called LISA. It's supposed to launch in 2035. But if the signals picked up in 2020 really came from cosmic strings, it could mean a huge breakthrough in physics. In this case, string theory would become the right framework for understanding the universe. It would completely change the way we think about the building blocks of our reality. On the other hand, even if the signals don't turn out to be from cosmic strings, this discovery would still be important. It would give scientists more information on what cosmic string signals might look like in the future. And while we're not yet at the point of time travel, the discovery of cosmic strings could take us one step closer to understanding the mysteries of the universe and maybe even the possibility of traveling through time. Now, time travel is a popular theme in science fiction, but in fact, moving forward in time happens naturally. Right now, you are traveling into the future at a steady rate of 1 second per second. However, scientists have discovered that this rate can change depending on speed and gravity. Einstein's special theory of relativity explains that time slows down as an object moves faster. The closer you get to the speed of light, the more slowly time passes for you, compared to someone who isn't moving at all. The general theory of relativity adds another factor: gravity. The stronger the gravitational pull, the more slowly time moves. Near massive objects, such as the surface of a neutron star, black hole, or even Earth, time runs more slowly than it does far away from these space objects. If someone were to stay near the edge of a black hole, where gravity is incredibly strong, only a few hours might pass for them, while thousands of years would go by for people on Earth. If they returned, they would have effectively traveled into the future. This is a real and scientifically proven effect. A real-life example of time travel, though on a tiny scale, can be witnessed in space missions. For example, this cosmonaut spent a total of 748 days aboard the space station Mir during 3 separate missions. Because Mir was moving at high speeds relative to Earth, it experienced time dilation. As a result, he aged 0.02 of a second less than had he stayed on the ground. Now, this difference may seem tiny, but it shows that time moves differently depending on speed and location. But while traveling to the future is scientifically possible, traveling to the past is much more complicated and controversial, and leads to logical paradoxes. Imagine you throw a billiard ball into a time machine. It travels to the past and collides with its earlier self. This prevents the ball from ever entering the time machine in the first place. A contradiction.
An asteroid drifts too close and the black hole seizes it. Gas twists and whirls and gravity starts pulling harder and faster. The accretion disk blazes and spins like a cosmic whirlpool. Radiation bursts out in violent flashes. The poor asteroid gets crushed and torn. Particles stretch into filaments, ripped by tidal forces. And then, in the blink of an eye, the event horizon swallows the asteroid, and it disappears from view. You're standing at the edge of the ultimate cosmic cliff, staring into a black hole. Sounds like instant doom, right? But scientists now say that, in theory, a human could actually explore a black hole and survive. The only thing is that once you go in, there's no coming back. It's a one-way ticket. So, how would it happen? It depends on the type of black hole. The thing is, black holes fall into two camps. There are stellar mass black holes, a few to a few dozen times the mass of the Sun. When a massive star, like 8 times heavier than the Sun, burns through its fuel, it doesn't just fade away. It collapses, rebounds, and explodes in a supernova. What's left behind depends on how massive it was. Medium big ones leave behind a neutron star, an ultra-dense remnant of a star. But if it was 20 times the Sun or more, it collapses all the way down into a stellar mass black hole. Most of the stellar mass black holes we've spotted are the clingy type paired up with stars. Some suck gas from their partner stars and light up in X-rays. We call those X-ray binaries. Thanks to these dramatic duos, we've found around 50 black holes in our galaxy so far. But scientists think there could be up to 100 million lurking quietly in the Milky Way. So yeah, we're surrounded. Next, there are supermassive black holes. These are behemoths chilling in the center of galaxies, millions to billions of solar masses. Almost every big galaxy out there, including our own Milky Way, has a supermassive black hole. Our galaxy's own heavyweight champ is Sagittarius A star. It tips the cosmic scales at about 4 million times the Sun's mass. That sounds huge, but compared to other galaxies, it's kind of a lightweight. Take the black hole in the galaxy Holmberg 15A, for example. It's got at least 40 billion suns worth of mass. To survive the jump into a black hole, you gotta pick this second supermassive one. Jumping into a small black hole is like being dropped into a cosmic blender. The outcome is instant, messy, complete spaghettification. Yep, that's a real science term. It's the process where something falling into a black hole gets pulled so hard by gravity that it's stretched out like spaghetti and then torn apart. But supermassive black holes are enormous, with gravity spread out over millions of miles. Falling into one wouldn't tear you apart immediately. Instead, you'd drift toward the event horizon, the invisible edge where even light can't escape. Picture it like a slow-motion water slide into the unknown. You'd still be fully aware, still intact, watching physics bending in ways you can't imagine. Why does size matter so much? A black hole with the mass of our Sun has an event horizon just under 2 miles wide. Now, remember that supermassive black hole at the center of our Milky Way? It has an event horizon more than 7 million miles wide. That difference matters because the gravitational pull between your head and your toes in a supermassive black hole isn't extreme. You could cross the event horizon without being stretched into a billion pieces. But the terrifying truth is, pass the event horizon and you're never coming back. From the outside, you just vanish. From the inside, time and space twist in ways no human experience could predict. You'd keep falling, conscious, intact, into a region of the universe that is completely, utterly unknown. So yes, humans could, in theory, explore a black hole, but it wouldn't be a thrill ride you'd ever tell anyone about. Once you cross the point of no return, your ultimate adventure will begin. What if you're going to be lost in the black hole forever, floating inside its mind-twisting core? Are you going to end once the black hole ends? Wait, do black holes even end? Decades ago, Stephen Hawking gave us a clue. Using math and physics, he showed that black holes aren't completely eternal. Over insanely long times, way beyond any human timescale, they slowly shrink. They emit a kind of hot radiation, now called Hawking radiation, and lose mass little by little. Eventually, a black hole becomes tiny. But what happens next? That part is still a total mystery. Scientists have some theories, of course. They're not proven because obviously we can't really test them. But they give us a way to guess what might be happening inside a black hole. One of the most developed ideas is called loop quantum gravity. It appeared in the late 1980s, and it tries to explain how space and time behave at the tiniest, craziest scales. According to LQG, something amazing could happen inside a black hole. As the black hole squeezes everything inward, eventually, the weird rules of quantum physics kick in. These rules create a super strong push that can fight back against the collapse. Basically, the black hole could bounce back instead of crushing everything into nothing. After that, space and time start acting normally again. But now the black hole is growing outward instead of shrinking. The coolest thing is that Einstein's theory says this is possible too. Scientists even have a name for it: a white hole. Think of a white hole as a black hole running in reverse. Kind of like tossing a ball. When it falls, it goes down, but when it bounces back up, it follows the same path in reverse. That's basically what a white hole does with space and time. Inside a black hole, everything gets sucked in. Inside a white hole, everything comes out. Nothing can escape a black hole, and nothing can get into a white hole. When a black hole has evaporated most of its mass, shrinking down to something tiny, loop quantum gravity suggests it can turn into a tiny white hole. Quantum effects make these little white holes surprisingly stable, so they could stick around for a while. Scientists sometimes call them remnants, because they're what's left after a black hole fades away. The jump from black to white hole is a sudden change, just like electrons jump between energy levels in an atom. If a spaceship crew watched from afar, a white hole would look almost exactly like a black hole. It has mass, it might spin, and dust and gas might swirl around its edge. But if they kept watching long enough, they'd see the impossible. The white hole would belch with sudden outflow of matter and energy. And then they would know for sure this isn't a black hole anymore. This is a white hole. A black hole has an event horizon, a point of no return. Once you cross it, you're gone. A white hole has the opposite. Its edge is a no-entry zone. Nothing from the outside can ever get in. Inside a white hole, things can come out and mix with the rest of the universe. But since nothing can get in, what's inside is completely cut off from the outside. Nothing that happens out there will ever affect it. But then, how does this filling of the white hole end up there? Could there be a tunnel connecting the black hole that swallows matter and energy with the white hole? And if so, could we leave through the white hole after safely entering the black hole? Sadly, that's very, very unlikely. You can't actually use some kind of bridge or tunnel to move between these holes. If you fall into a black hole, you'll eventually crash into the singularity at its center, even if you survive the initial journey through the event horizon. In any case, so far, these are just speculations, since black holes remain mysterious and unreachable, and we haven't even proven the existence of white holes yet.
It's official. Official. A day will no longer last 24 hours. Earth's now spinning faster, literally, and our days are going to get shorter. At the moment, it's believed that the shortest day happened on July 10th, 2025. It was shorter not by much, just a fraction of a second, 1.36 milliseconds according to most sources, but still. And all because of the moon's position messing with Earth's rotation, just enough to speed things up. If it turns out to be not a one-time thing and Earth keeps spinning faster, it could be the start of a big mess. All our time stuff like GPS, the internet, atomic clocks, even how countries keep time, depends on the day being 24 hours. But if the planet speeds up, those systems could totally freak out. Clocks would get all out of whack, and anything that needs perfect timing could go sideways. We're talking about more than just a few lost seconds. This could shake up everything. Flights, money transfers, basically how we live day to day. We'll have to rethink how we measure time. Are you ready for that kind of chaos? Now, normally a day is 24 hours, or 86,400 seconds, because that's how long it takes for the planet to do a full spin. But Earth's rotation isn't always stable. A bunch of things influence it, like where the sun and the moon are or how the planet's mass is balanced. Earth is like a giant spinning top, and anything can throw it off rhythm. But our planet has been slowing down for a long, really long time. Because according to scientists, about 1 to 2 billion years ago, a day only lasted 19 hours. Not because the planet was lazy or anything. Nope, it was the moon's fault. It was way closer to us back then. Its gravity had a stronger pull, and that made Earth spin faster. And that faster spin meant shorter days. The thing is, the moon is slowly drifting away from Earth, and as it does, Earth's rotation slows down, and our days get longer over time. But during that billion-year window, something weird happened. The moon kinda just hovered at a certain distance. It wasn't moving out, it wasn't pulling harder. It was like it paused. And that pause locked us into 19-hour days for what scientists are now calling a boring billion. It was a time when pretty much everything on Earth slowed down. Tectonic activity was stable, the climate wasn't doing anything weird, and even life kind of plateaued. Now, let's get into the sciencey part. The moon's gravity controls our ocean tides. That's what slows down Earth's spin. But the sun pulls on Earth too, just in a different way. When sunlight hits Earth's surface and heats it up, that creates what's called solar atmospheric tides, and those can actually speed up Earth's rotation. Right now, the moon's gravitational tides are about twice as strong as the sun's atmospheric tides, which means the moon is in charge when it comes to Earth's spin. But back in the boring billion, the sun and moon were basically in a tug-of-war with equal strength. This phenomenon is called tidal resonance. It's like Earth hit a cosmic pause button. If the moon hadn't backed off, we might still be living in a 19-hour day world right now. These days, the moon is still drifting away from us, and because of that, our days are slowly getting longer. Until lately, things have gotten weird. In the last few years, scientists noticed that Earth hasn't been sticking to schedule. In fact, it's been spinning faster, and I mean record-breaking fast. Back in 2020, Earth started picking up the pace more than it had since scientists started clocking it in the 70s. Then came July 5th, 2024, the shortest day ever recorded. We lost 1.66 milliseconds. Not a big deal if you're just watching videos on YouTube, but on a planetary scale, it's kinda huge. Now, we get back to July 10th, 2025. On that date, the moon was sitting way up near the poles, very far from Earth's equator. And that changed the game. When the moon is hanging out closer to the poles, it messes with Earth's rotation and makes our days a little bit shorter. That kind of change isn't unusual. Earth's spin has always had some ups and downs. But today, the moon isn't the only factor. According to NASA, human activity is changing how Earth spins too. Between 2000 and 2018, moving ice and pumping groundwater around the planet shifted enough mass that it added 1.33 milliseconds to our days per century. Natural disasters can mess things up too. Remember the massive earthquake that hit Japan in 2011? It actually shortened Earth's day by 1.8 microseconds. Just one quake, one microjolt to the planet's schedule, but the consequences were catastrophic. On March 11, 2011, at exactly 2:46 p.m. local time, a huge earthquake hit off Japan's east coast. We're talking magnitude 9, one of the biggest quakes ever recorded. The epicenter was about 80 miles from Sendai and over 230 miles from Tokyo. Japan's main island shifted 8 feet. Yes, the ground moved and whole cities literally slid, but it didn't just shake buildings and trigger a tsunami. The quake was so strong it redistributed Earth's mass, like shifting weights around on a spinning top. When you do that, the top spins differently. Same deal with Earth. The movement of tectonic plates was enough to tweak the whole planet's rotation. The thing is, the earthquake moved land and shifted Earth's figure axis. That's the axis our planet's mass balances around, by 6.5 inches. That's separate from the north-south spin axis, which we rotate on daily at about 1,000 miles per hour. But still, that shift was enough to make Earth wobble differently as it was spinning. It didn't tilt the entire axis in space. Only stuff like the Sun or Moon's gravity can do that. But it was still a major shakeup, no pun intended. And it wasn't the first time this had happened. The 2004 Sumatra quake, a staggering magnitude 9.1, sped up Earth's spin and cut 6.8 microseconds off the day. Chile's 2010 quake took off another 1.26 microseconds. Every time one of these mega quakes hit, it's like Earth gets a tiny jolt, spinning just a hair faster. And it might not be over. For example, that March 11 quake unleashed more than 80 aftershocks that were magnitude 6.0 or higher. Long after, some of those aftershocks were still tweaking the day length. It was very subtle, changes in millionths of a second, but real. But the thing is, even the seasons can mess with how fast Earth spins. A geophysicist from the University of Liverpool has explained it like this. There's way more land in the northern hemisphere than in the south. So, during northern summer, trees grow leaves, and that leaf mass moves upward, farther from Earth's center. And it sounds pretty harmless, right? But no, that tiny shift actually slows down our planet's spin, just a bit. Think about a figure skater arms in, they spin faster. Arms out, they slow down. Same with Earth. When its mass shifts away from the core, it rotates more slowly. So yeah, in the summer, Earth literally chills a bit, spin-wise. Now you don't panic about your day suddenly feeling longer yet. Your clock is still gonna say 24 hours. That's just how our timekeeping works. As for these differences, they're milliseconds. You'd never feel it. But the problem is that over time, it all adds up. If the planet ever spun slow enough that we were off by more than 0.9 seconds, then we'd have to do something. That's when the International Earth Rotation and Reference System Service steps in. These are the people who keep tabs on Earth's spin, and if things drift too far out of sync with our clocks, they throw in a leap second to fix it. Yep, they literally add a second to the clock every now and then to keep Earth time on track. It's like the universe's version of a software update. In any case, with the moon slowly drifting away and Earth calming down, the fact that our planet is suddenly picking up speed, even just a little, makes experts and ordinary people raise their eyebrows. It's a reminder that even something as basic as a day isn't set in stone. The planet's moving quicker. Time is literally slipping. Something's shifting. Look at this giant donut-shaped region far away from Earth, beyond the orbit of Neptune. We're talking about a distance of more than 2.5 billion miles. It's the Kuiper Belt, and something eerie and bizarre is happening there. Dwarf planets and other small objects dwelling there refuse to cluster together. Instead, they follow particular orbits, which is weird. The reason might be a large, mysterious planet hiding beyond Pluto. Its gravity might be messing up the orbits of those Kuiper space bodies. Hear me out. Our solar system is made up of the Sun and everything that goes around it because of the star's strong gravity. This includes the 8 main planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. There are also smaller things like moons, asteroids, and Pluto. For a long time, people thought Pluto was the 9th planet, but when it was reclassified as a dwarf planet, scientists started looking for a new Planet X. Did they have a thing about odd numbers or what? And guess what? Some really think there might be a big, icy planet hiding far, far away beyond Neptune. This mystery planet is often called Planet 9. Now, Planet 9 hasn't been seen yet, but scientists think it might be out there because of some tiny, faraway space rocks called etnos that move following bizarre, confusing paths. These paths seem to be grouped together and tilted in a way that doesn't happen by chance. This could mean there's a hidden planet pulling them into place with its gravity. If Planet 9 is real, it might be 5 to 10 times heavier than Earth. It would also be super far away, hundreds of times farther from the Sun than Earth is. Over the years, scientists have guessed different distances for its orbit, and the newest guess in 2025 says it could be about 290 times farther from the Sun than Earth. There are some cool ideas about where Planet 9 came from. It might have started as a big planet that Jupiter once kicked out of the inner solar system, or it might have come from another star or even wandered around space on its own before getting caught by the Sun's gravity. Even though scientists have looked really hard using powerful telescopes, no one has actually seen Planet 9 yet, and so far, its existence is still just a theory. But recently, a group of researchers tried something clever. They used data from two special space surveys called IRAS and ACARI. These two looked at the sky in invisible light, far infrared, about 23 years apart, which is helpful because Planet 9 is supposed to move very slowly. The team focused on a special list from ACARI, which is better at finding faint, moving things in space. They guessed how bright Planet 9 might be and how fast it might move based on how big, far away, and cold it could be. Then they looked for matching blips in the sky that were seen by both IRAS and ACARI, but not in the exact same spot. That's because a real planet would have moved a little over 23 years, and they indeed found 13 possible matches that could be Planet 9. Their estimations were based on how far away the object seemed to be, 500 to 700 times farther from the Sun than Earth, and how heavy it might be, which is 7 to 17 times Earth's mass. After looking very carefully at all the images, they narrowed it down to one really good candidate. The two detections weren't in the same spot in both surveys, and the way they appeared in the ACARI map matched what you'd expect from a slow-moving object. It showed up on one date and wasn't there 6 months earlier, but of course, there was a catch. Apparently, the old data isn't good enough to figure out the exact path of the potential planet. So, the team wants to do new follow-up observations using a special camera called DCAM, which is really good at spotting faint, moving objects. That way, they can find out if this candidate is really Planet 9. Additionally, it can help us learn more about how our solar system works and how it formed. If Planet 9 is ever discovered, it would totally change the way we understand our solar system. It could explain why some far-out space rocks in the Kuiper Belt tilt weirdly. The thing is, most planets go around the Sun in a flat-ish circle, but those faraway objects are tilted about 20 degrees. Planet 9 might be the reason why. Next, we'd probably find out why those tilted objects seem to point the same way. Their orbits are grouped together in one direction. A big hidden planet's gravity could be hurting them like sheep. There are also some strange tilted objects super far away. They don't make sense unless something big, like Planet 9, is tugging on them. A few space rocks orbit the Sun backward between the big planets, which is kinda the wrong way. That's super weird unless something big is messing with them. Some far-out Kuiper Belt objects keep crossing Neptune's path and haven't been flung away. That's because Planet 9 might be helping keep their orbits stable over a long time. Another cool thing is that if Planet 9 existed, it would be a super-Earth. a kind of planet we see a lot around other stars, but we don't have in our solar system yet. So finding one here would make our solar system more like the others out there. Throughout history, people have been wondering if there could be hidden planets far beyond Neptune, even before Pluto was found. Back in 1880, a guy named George Forbes guessed there might be 2 unknown planets way out there, one about 100 times farther from the Sun than Earth, and the other about 300 times farther. He thought these mystery planets might be pulling on some comets and changing their orbits, kind of like how Jupiter does with the comets near it. In 2004, scientists found a weird little world called Sedna. It had a strange path around the Sun that didn't seem to be affected by any of the known planets. Its closest point to the Sun, called perihelion, is way too far for Neptune to be the reason. This made some scientists wonder if Sedna got pushed into its path by a hidden planet, maybe even something as big as Earth or bigger. Others thought maybe it was a star that flew by a long time ago, or another star that formed near ours. Then, in 2014, another odd object was discovered. It had a very similar orbit to Sedna, which made people even more suspicious that there could be something big out there messing with their paths. This kicked off a new round of the Planet X or Planet 9 hunt. At a meeting in 2012, a scientist named Rodney Gomez said that maybe there was a big, hidden planet around 1,500 times farther from the Sun than Earth. He thought it could explain the orbits of other odd objects, like some far-out comets and centaurs, small bodies that wander among the giant planets. At that time, those who supported the Planet 9 theory believed that if it existed, it would move around the Sun in a huge, stretched-out circle called an elliptical orbit. It would be about 400 to 800 times farther from the Sun than Earth is, about 13 to 26 times farther than Neptune. If it really had that kind of orbit, it would take around 10,000 to 20,000 years to go around the Sun just once. Plus, if it indeed orbited the Sun, it wouldn't follow the same flat path as the other planets. Its path would be tilted by about 15 degrees to 25 degrees. The farthest point in its orbit, called aphelion, would be in the direction of the Taurus constellation. As for the closest point, it would point towards Serpens, Ophiuchus, or Libra. As for the composition of Planet 9, it would probably be a lot like Uranus or Neptune. It would have a thick atmosphere made of hydrogen and helium, and it would be super cold, negative 375 degrees Fahrenheit. Its core would be made of iron, and its middle layer would be full of rock and water ice. At the same time, if the planet was smaller and denser, then it might be more like Earth, with a rocky surface instead of a gassy one. According to a scientist named Mike Brown, if Planet 9 was real, a space probe would reach it in about 20 years if we used a powerful slingshot path around the Sun.
The red, parched earth under your feet is shaking. Large cracks are opening in the ground, threatening to swallow you. But unlike on Earth, these quakes aren't coming from within the planet. A threat coming from space is triggering them. Scientists have made a shocking discovery about Mars quakes. By using AI and NASA's InSight data, they found out that some of those tremors are caused by meteorite impacts. It means that Mars gets hit 2.5 times more often than we thought, and new craters are forming all the time. But the scariest part is that these impacts don't just shake the ground. They send powerful shock waves deep into the planet, revealing a hidden seismic highway and an unstable interior, unlike anything we imagined. This changes everything we thought we knew about Mars. So now, the big question is, what else is lurking beneath the surface? But let's follow scientists' train of thought first. They took Marsquake data from NASA's InSight lander and compared it with fresh impact craters spotted by the Mars Reconnaissance Orbiter. That's when they discovered that some impacts create a seismic highway through the mantle instead of being absorbed by the crust. Even though NASA shut down InSight in 2022, its data is still precious. The lander, which placed a seismometer on Mars, recorded over 1,300 Mars quakes, some caused by underground rock cracking under heat and pressure, others, apparently, by meteoroids slamming into the surface of the red planet. By studying how seismic waves move through the crust, mantle, and core, scientists keep piecing together Mars's deep structure. In the past, researchers already linked impact craters with seismic data. But these new studies are the first time when a fresh impact has been connected to quakes detected in Cerberus fossae. That's a highly active region 1,000 miles away from InSight. Scientists have discovered this 71-foot-wide crater much farther from NASA's InSight lander than expected, if we consider the strength of the seismic waves it produced. Mars's crust was thought to absorb most of the energy from impacts, which would limit how far seismic waves could travel. But the analysis of this crater revealed that, instead of getting dampened, the waves took a more direct and deeper path through the planet's mantle. This unexpected finding suggests that Mars has a seismic highway, which allows quakes to spread much farther than previously believed. Now, the InSight team will need to reassess their models of Mars' internal composition and structure. And then, we might better understand how impact-generated seismic signals can reach such depths. Manually sorting through the vast amount of data would have taken years. But luckily, these days, there are new tools, and scientists can go from tens of thousands of images to just a few in a matter of days. So, researchers focused on finding craters within approximately 1,800 miles of InSight's location. Their aim was to identify those that formed while the lander's seismometer was active. By comparing before and after images from the context camera over time, they identified 123 fresh craters to cross-reference with InSight seismic data. Out of those, 49 craters were potential matches for quakes detected by InSight seismometer. And after conducting some more analysis, the team decided that the 71-foot Cerberus fossae impact crater was the main finding. This discovery is likely to help scientists differentiate between signals from internal quakes and those caused by meteoroid impacts. Initially, they believed that Cerberus fossae produced a lot of high-frequency seismic signals linked to quakes originating inside Mars. But the new data suggests that some of this activity may have been caused by impacts, not internal processes. Another mystery scientists haven't been able to crack for 50 years is why Mars is split into two very different halves. But thanks to recordings of Mars quakes, they may have finally found the answer. Since the 1970s, researchers have known that Mars has two distinct regions. The northern lowlands cover about 2/3 of the planet's northern hemisphere, and the southern highlands make up the rest. The southern highlands sit about 3 miles higher than the northern lowlands, and the crust, the planet's outer layer, like a shell, is thicker in the south. This strange divide is known as the Martian dichotomy. There are two potential explanations for this imbalance. One theory suggests that an unknown internal process within Mars created the difference. The other claims that a massive collision, probably with a moon-sized space rock or several smaller impacts, once reshaped the planet's surface. But Mars' surface is extremely old. That's why pinpointing exactly what happened has been difficult. But now, a new study, published on December 27, 2024, has used Mars quake data from NASA's InSight lander to figure out whether the cause of this difference lies deep inside the planet. InSight was positioned near the boundary between the northern lowlands and southern highlands. Its mission included recording seismic data from Mars quakes, which travel through the planet's mantle, the rock layer beneath the crust. So scientists compared how these waves moved under both lowlands and highlands. They looked for differences in the planet's deep interior. It turns out that the seismic waves lost energy much faster when traveling through the southern highlands. It means that the mantle beneath this region is significantly hotter than in the north. It's compelling evidence that internal planetary forces, rather than an external impact, caused Mars' unusual split. The research team believes that the temperature difference between Mars' two halves can be traced back to ancient tectonic activity. It once shaped the planet, but later stopped. At some point in the past, Mars had moving tectonic plates, like Earth's. As these plates shifted, they, along with the molten rock beneath them, could have created the Martian dichotomy. But eventually, the movement stopped, leaving behind what scientists call a stagnant lid. That's a thick, immobile layer over the planet's molten interior. If this turns out to be true, it might mean that the mantle beneath the southern highlands is still pushing upward, while the mantle under the northern lowlands is sinking deeper toward the planet's core. This ongoing process could explain why Mars' crust is thicker in the south. At the same time, we can't completely rule out the idea that an external impact created the dichotomy. Some recent studies suggest that a giant collision could still be a possible explanation. To solve this mystery for good, scientists will need more Marsquake data and detailed models of how Mars originally formed. By the way, if you ever decide to visit Mars, you might come across the hero of our video today, the InSight lander itself. It was supposed to launch in March 2016, but a problem with one of its instruments caused a delay. It was a vacuum leak in the seismometer. NASA rescheduled the launch for May 2018, and the issue was fixed in the meantime. But this delay increased the total cost from $675 million to $830 million. Still, InSight successfully landed on Mars on November 26, 2018. But over time, dust built up on its solar panels, making it harder to recharge. The InSight lander runs on solar panels and batteries, but it needs occasional wind gusts, called cleaning events, to clear dust from the panels. Unfortunately, the place where InSight landed didn't get enough of these winds to keep the lander fully powered. By February 2021, during the Martian winter, thick dust had covered the panels, and they were only producing 27% of their full capacity. To save power, NASA started putting InSight into hibernation mode, shutting down instruments gradually to keep its electronics warm. They hoped better weather would allow the lander to recharge and wake up by July 2021. In May 2021, the team found a clever way to restore some power by using the lander's arm to move sand onto the panels, helping the wind clean off some of the dust. But eventually, InSight was only generating 1/10 of the power from the sunlight than it did right upon arrival. In July 2022, NASA put it in low power mode to keep detecting Marsquakes. The lander kept operating until December 2022. On December 20th, NASA announced that InSight had lost contact with Earth on December 15th, and the mission officially ended on December 21st, 2022.